Hello again. In the previous lesson, we performed matrix operations. We found inverse matrix, and we used an inverse matrix to solve a system. In this lesson, we will calculate determinants and use Cramer's rule to solve two variable linear systems. So let's begin with the quick rules. So first of all, for the matrix ABCD, the determinant is AD minus BC. All right. So again, for this, the determinant is this here, which is what we looked at in the last lesson. A determinant of zero means that the matrix is singular and has no inverse. Cramer's rule uses d, dx, and dy. Okay, Cramer's rule uses d, dx, and dy to solve two variable linear systems. Cramer's rule applies only when d is not equal to 0. Okay, the determinant is one number calculated by the square matrix, and for a 2 by 2 matrix, we need to multiply along the main diagonal, right? All right, so let's go ahead and get started. So find the determinant of a equals 4. Okay, so find the determinant for this. For a 2 by 2 matrix, in order to do this, it's simply determinant of A, which is AD minus BC. So we need to identify the entries. So we'll say A is equal to 4, B equal to -2, C is equal to 3, and D is equal to 5. All right. So essentially substituting the information in here, we have 4, 5 minus a -2 and 3. All right, so that's going to be 20. 4 times 5 is going to be 20. And then -2 and 3 is going to give me a -6. That's going to be minus -6. This becomes a plus, so this is 26. So the determinant of A is equal to 26. But be careful with this negative entry, okay? Subtracting a negative product becomes addition. Example number 2. Example number 2, it says for the matrix B is equal to 6, 9, 2, 3, compute the determinant of B and state whether B has an inverse. So first of all, we want to start with the determinant of B. The determinant of B, of course, is AD minus BC. And those values are A would be 6, D would be 3, minus 9, and 2. That's 18 minus 18, which equals 0. So the determinant of B is equal to 0. So since the determinant is equal to 0, the matrix has an inverse only when the determinant is non-zero, right? So what we would say is, okay, so only when the determinant is like a non-zero number, then the inverse exists. If this happens, then the inverse doesn't exist, okay? The matrix essentially is not invertible, right? A matrix with a determinant of 0 is called singular, right? So determinant B is equal to 0, right? That being the answer. So its rows or columns are dependent, so the matrix cannot be reversed with an inverse. That's essentially what it says. All right, pause and try the problem in the bottom. Okay, so first of all, I want to start with the coefficient matrix. All right, the x coefficients are, excuse me, the x coefficients right here are 2 and 5. And then the y coefficients are 3 and -1. So what we need to do is say d is equal to 2, 3, 5, and -1, right? Because, and this is essentially writing the determinant matrix for D, okay? So the way you need to think about it is D uses the coefficient matrix, D sub X replaces the X column, and then D sub Y replaces the Y column of constants, right? Now we need to form DX. So the script X contains, or excuse me, tells us to replace the X column. So the constants are 7 and 9, and then we want to keep the Y column unchanged. All right. So this would be 7, 9, 3, -1. Okay. And just to reiterate, so we started with the coefficient matrix, and the X coefficients were 2 and 5, and the Y coefficients were 3 and -1. Okay. So 2 and 5, 3, -1. And then the dx, the subscript x tells us to replace the x column. So the constants are 7 and 9, which is here, 7 and 9. And then the y stays the same, which is 3, -1, right? And then now we want to look at dy. So what in dy, we want to replace the y column with the constants and then keep the x column unchanged. So replacing would be 2, 5 and 7, 9. Okay, notice the constant stays the same and the x changes. Okay. So the final step essentially is to write these out, right? When you're told to, when it says for 2x plus 3y equals 7 and this, write the determinant matrix. So for this, what we essentially did was we took the coefficients to 3, right? As you can see for the x, and then the y was 5, -1. Okay, 5, -1. All right, so again, the x would be 2, the x's would be 2 and 5, which is what we got here, and then 3, -1 would be y. So the way you can look at it is this is the x, this is the y, and I might have misspoke, but excuse me. So this is the x, which is 2, 5, and then the y is 3, -1. And here 7, 5 or 7, 9, which is the constant, right? And then 3, 1, obviously you see 3, 1, so that would be the y. And then here we use 2, 5, which is the x, and then the 7, 9, which is the constant. Okay, so that's how these are set up, and it says do not solve yet. All right, let's go over to example number 3. Example number 3, it says using Cramer's rule. All right, so use Cramer's rule for the following: 3x plus 2y equals 12 and x minus 4y equals -10. Cramer's rule is, in Cramer's rule, what we need to do is we need to write x equals dx divided by d, and y equals dy divided by d. Okay. First, we need to calculate d using the coefficient matrix. Okay. So d is, in this case, 3, 3, 1, right? Because we have, that's x and y. So y would be 2, -4. And then we need to find dx. So if we remember, this is what we're using down here, right? And what I want to do here is, before I get to the dx, right, I want to use AD minus BC, okay, for this one right here. So for here, we want to use AD minus BC, which essentially would be 3, -4, -2, and 1. So D would be equal to -14. Okay. So we know what D is. D is equal to -14. Now, since D is not equal to 0, Cramer's rule may be used. All right. Now, again, if D was equal to 0, we can't use Cramer's rule. So therefore, we're going to move on to this. So I kind of got ahead of myself because I already knew what this was going to be. All right. So D of X, we want to replace the X column with the constants 12 and 10. So this will be 12, -10, right? So you replace it with the constant, and then we want to keep the Y the same, which is going to be 2, -4. Then we evaluate dx. So the determinant, which is AB minus BC, or AD minus BC, which is going to be 12, -4, -2, -10. And that is going to be -48 plus 20, which is -28. Okay. So again, dx is equal to -28. Now we need to calculate x, right? Because we have dx and we also have d, all right? I'll say this is d. Okay. So we can calculate this over here. So I'm going to put it up here. Equals dx over d, which is -28 and -14, also known as 2. So x is equal to 2. Now we need to calculate dy. So we're going to use b minus ad. Okay, typo. dy. And that is going to be 3, 1, 12, -10. Okay. And again, that's 3, 1. So 3, 1. So that's the x's and then the constants. Okay. Whereas this was the constants and the unchanging y. Okay. And so this shows you how to remember it. D is xy, dx is constant y, dy is xc. All right, so dy is 3 times -10 minus 12 times 1. Okay, 3 times -10 minus 12 times 1. Then that result is, let's see, -30 minus 12 would be -42. Okay, so now we can solve for y. So y is equal to d sub y over d. D sub y is -42 over -14, which is equal to 3. Okay, so the ordered pair of xy is equal to 2, 3. And then we can check the solution. We can substitute this into one of the equations. I'm going to substitute into the first one. So 3, 2 plus 2, 3 equals 12. 6 plus 6, 12 equals 12. Okay, checks out. And then we can check the second one as well. So that would be x, which is 2, minus 4, y, which is 3, equals -10. That's 2 minus 12 equals -10. And so this is going to check out as well, -10 equals negative 10. Okay, so this checks out as well. All right, example number 4. A system has coefficient determinant equals D equals 0, which is the determinant equals 0. Explain what this tells you about Cramer's rule and what additional work is needed to decide whether the system has no solutions or infinitely many solutions. Cramer's rule requires division by D, right? So the formulas are x equals d sub x divided by d, and y equals d sub y divided by d. Okay. So and again, Cramer's rule requires that we divide by d. So if d is equal to 0, then Cramer's rule cannot be used. But d equaling 0 alone does not tell us whether the system has no solutions or infinite solutions. We essentially need additional work. We could use elimination, substitution, or even row reduction or whatever equations that we have. But nevertheless, when d is equal to 0, we need to use elimination, substitution, or row reduction. Okay. If the work produces a contradiction like the one that we saw in our previous work, which is like 0 not excuse me 0 equaling 5 or 0 being not equal to 5, then that essentially has no solutions. A contradiction is when we have 0 being equal to a non-zero number. Okay. So there are no solutions in that case. If the work produces a true statement, like if it produces something like 0 equaling 0, which is true, then that equation may represent the same line, giving infinitely many solutions. And then this is also called the called identity. Okay. Because 0 equaling 0 or 5 equaling 5, that's identity. So therefore, a 0 determinant tells us that the coefficient matrix is singular, and Cramer's rule does not apply in this case if it is not equal to 0. Capstone, what is a common mistake? So a student forms d sub x by replacing the second column of the coefficient matrix with the constants. Correct the setup and explain how dx and dy are formed. So the subscript tells us which variable column to replace. For a system that is written like a sub 1x plus b sub 1y equals c sub 1, and a sub 2x plus b sub 2y equals c sub 2. The coefficient determinant is d or a sub 1, a sub 2, b sub 1, b sub 2. Okay. That's how we need to understand it. So a sub 1, so the x's align and the b's align. So that's how we understand this. The coefficient determinant would be this right here. Right. For d sub x, we want to replace the x column. For d sub x, we want to replace the x column with the first column, or excuse me, replace the x column with the first column with the constants. So the way that would look is c sub 1, c sub 2, b sub 1, b sub 2. Okay. So c sub 1, see we have the constants here. We're replacing that with the x. And then we have b sub 1, b sub 2. So that So the y's essentially remain the same. For dy, we want to replace the y column, which is the second column, with the constants. So d sub y would look like this. A sub 1, A sub 2, C sub 1, C sub 2. Okay, and again, A sub 1 is the x, and then we're replacing y with the constants. Okay, so the correct rule is d sub x replaces the x column, d sub y replaces the y column. Okay, so the student essentially reversed the replacement rule. The subscript always identifies the column being replaced. So notice this right here tells me to replace the x. This right here tells me to replace the y. Okay, let's review. So again, for the determinant of A, or A, B, C, D, the determinant is AD. As a matter of fact, you can't see that. So for A, B, and C, D, the determinant is AD minus BC. And the determinant is equal to 0. Excuse me, if the determinant is equal to 0, the matrix has no inverse. Okay, if it's equal to 0, the determinant has no inverse. Okay, so we can't have no inverse exists. We also looked at Cramer's rule. Cramer's rule is x is equal to dx divided by d, y is equal to dy over d. And in Cramer's rule, d cannot be equal to 0, which is obvious. And you need to remember the fact that dx and dy, this shows you what to replace. Replace x, replace y. And then again, just for the record, if you're, x would be found by using this, y would be found by using this. And you cannot have d equaling 0, because if this happens, then we cannot use Cramer's rule. All right, this completes video 17, part 3, determinants in Cramer's rule. Thank you for watching, and I hope to see you in the next one.